good morning EIR students. We're in the last lecture for chapter 8, chapter 8.7, and this is also the last little DC bit we're going to do. After this, we're going to start finally with AC circuits. So chapter 8.7 is on general second order circuits. If you recall back in the first lecture of chapter 8, I showed you circuit diagrams where you have only resistor or capacitors or resistors and inductors in the circuit, and you thought, oh, that might just be an RC circuit or just a RL circuit, but you can't combine the two. So we're going to look at one of those examples. So we're only going to work through one practice problem 8.10. The PDF is on ClickUp already under lecture notes, along with practice problem 8.9. So you might want to download that first, and if you can, perhaps print it out, and then you can make notes on it. This practice problem is really just simply too long, and my board is too small, and the time not enough to complete this in one lecture. So even when I do this lecture in a normal class situation, I just work off the PDF because there's just no time to write everything on the board. It's quite a lengthy process. So I'm just gonna, for this lecture, I'm just gonna do it from the PDF. So you're welcome to make notes from there. Okay, before I do that, perhaps I think I just want to share something with you. So my daughter decided for the door I need a nice I'm busy recording poster, so we stick this on a bedroom door when I'm busy, so then everybody knows Daddy is busy recording. Okay, let's go over to this one, chapter 8.7. Now there is a nice step by step. There are 4 steps. Let me just get on the right page on this screen. There we go. Now you can see the hand. So they've got 4 steps listed there, or the process, the process that you need to follow. So it's pretty nicely described. I can't really add to that. What I just did for myself is I just broke up step number 2 into 4 separate steps. When you read it, you'll see there's 4 sub-steps there. I'm not going to talk through it now. We're going to you're going to see those steps explicitly stated in the example that we're going to work through. Alright, so let's, instead of going through the theory, let's immediately jump to practice problem 8.10. So first I just want to look at practice problem 8.9, just the circuit. So in this case, there's a capacitor and there's an inductor, but it's a weird type of circuit. It's not a parallel, it's RLC, it's not a series RLC, because the moment that you switch in that source, then you've got 2-3 parallel branches there, but the problem is you can't simplify the circuit to be either series or either parallel. So I've worked it out. You can see how we did that problem. Then the one I want to do is actually a circuit that they showed in the beginning of the chapter, practice problem 8.10, this one. Let me just zoom in a little bit. So initially, this might seem, or you might think that, hey, this is just an RC circuit because there's just resistors and capacitors. So what makes this not an RC circuit? The problem here is you can't combine this capacitor, the 1/3 farad and the 1/2 farad, into one capacitor because of this 1 ohm resistor sitting there. Alright, so they have to remain separate, and you've got 2 energy storage elements. So what we need to go and do, and what they're asking for, is we need to find the response or an expression for V out. So the voltage across this resistor. Now that's a rather nasty one, because what is V out? V out is V1 minus V2. Let's go over to this one. So if we want an expression for V out, the voltage across that resistor, it means we actually need an expression for V1 And once we have an expression for V1 and for V2 also, then I need to subtract the 2, and then I get that expression. So we need to go and figure out what is the voltage at node 1 over there, and what is the voltage at node 2. Do they actually number those nodes? Yeah, so there's V1 and V2. I don't know why I didn't put them there. V1 and V2. So we've numbered those nodes. And then on the left, what we've got there is the source, and we see there's a step response function, step function. So this voltage source is off, in other words, a short circuit before time 0, and then it kicks in at time 0. So step 1 in that 4-step process that chapter 8.7 talks about is finding the initial conditions. And you'll see it's the order of things is very much like we did for the previous bits. But you'll see where the difference comes in. So we find the initial conditions. For what do we need to find the initial conditions? We need to find the initial conditions for the voltages V1 and V2, because that is the two expressions that we are going to need. So it's not just V1 or V2, it's both of them. Sorry, you can't see there. So we need to find the expression for the voltage and their derivatives. Okay, so you'll see there the expression for just the voltage. So before time 0, we know that V1 0 plus is V1 0 minus. So what does the circuit look like at time 0 minus? Well, as we mentioned, the source is a short circuit. Capacitors after a very long time is a open circuit. And then we effectively just do a KVL. So we didn't write that down. I didn't. So if you just do a KVL in that loop and then in that loop, you end up with them having to be 0 volts. Because you don't have, in the open circuit scenario, there can't be any current flowing through that resistor or that resistor. No currents, no voltage drops. So there's 0 volts plus 0 volts plus the capacitor voltage must equal 0, and the same for that loop. So both of those voltages have to be 0. In reality, where it would have started, perhaps let's just talk about that. Let's say at time minus infinity, the capacitors were charged, and we make a short circuit there. Both those capacitors will empty themselves. This capacitor will empty itself through that resistor, for argument's sake, and that capacitor will empty itself through that resistor. So they empty themselves, they become 0 volts. Okay. So that's the two initial conditions for the voltage. Then we need the initial conditions for the derivatives. So now we draw the circuit for time 0 plus, and that voltage source is now on. And the moment that that voltage source, suddenly I've got a nose tickle. The moment that that voltage source is on, you've got current that starts to flow, and that capacitor starts charging up, and that capacitor starts charging up through that resistor. So we want to figure out what is that rate of charge. How fast will they be charging the moment that switch closes? There's no switch. The source switches in. So what is dV1? That capacitor dt. So it's I1 over C. So what is I010 plus? What is the current that's going to flow there at time 0 plus? That we need to figure out. So we do a Kirchhoff's current law at that point. Now I've just given the current names. So that's I, the total current, I1 flowing through capacitor 1 from node 1, and I2 is the current flowing through capacitor 2. And now remember, the direction of the currents are very important. In the example here, they just put a V1 and V2, but they've put down a ground node as well. So this whole node at the bottom, that's 0, which means the plus is at the top for this capacitor, and the same for this capacitor. The plus is at the top. So there's the ground node, so I know it's plus, minus, so the current needs to go down. But because this capacitor and this resistor, they're in series, so I've got I2 in that whole branch over there. So I've got I2, I've got an I1, and I've got the total current. So the total current that comes in at that node must equal I1 and I2, the two currents going out. Okay, so which current am I actually looking for? Well, we're going to need both I10 plus and I20 plus. So we've only written out dv1 dt0 plus, but we know we're also going to need dv2 dt0 plus, which will then need I2 at time 0 plus. So we need to solve for both of these. Now initially we're going to start with I total, I0 plus, that one over there. For that we can write down an expression. We know it's 35 minus V10 plus. So Ohm's law, it's 35 volts on that side of the resistor. V1 at time 0, we know it's 0 volts. So we can calculate the total current that's coming in, and that's going to be, now then, 35 over 1 gives me 35 amps. I20 plus, what's the initial voltage there? It's the same current flowing through that resistor. So again, Ohm's law, the current is flowing left to right, so it's V1 minus V2 over the 1, which we know it's 0 minus 0, and that gives me another 0 amps. So now we've got I0, we've got I2, and now we can calculate I10 plus, which is going to be just 35, because now you've got that I needs to be I1, because we know I2 is a 0, so we know I1 has to be 35 as well. So for that split second, just when that switch closes, all the current is going to flow through that capacitor. But just for that split second, the moment that that capacitor just gets a little teeny bit of charge, then we're going to see you're going to start getting current through I2 as well. So that, remember, it is only for time 0 plus, just that instant after the source switched in. Okay, so now we can calculate dv1 dt. So it's 35 divided by the 0.5 farad, and we get 70 volts per second. But because I20 plus is 0 initially, just the rate of charge at time 0 plus for capacitor number 2 is 0 volts per second. And then we also need to find the final condition. So we're all still busy with step 1, the initial, I should have written there, and final conditions. Okay, so time at infinity, what are the voltages going to be after a very long time? Okay, this we've covered a lot in previous example. I'm not going to go through detail, but both of them has to charge up 35 volts. At the end of the examples, I'll show you a water dam version of the same problem, an analogy. So they both have to charge up to 35 volts, because if V1 is at 35 and V2 is at 35, your voltage potentials are the same on V1 and V2, and if there's no potential difference across that resistor or that resistor, because it's 35, 35, 35, you won't have any currents flowing, so the capacitors won't charge any further. Right, so that's step 1, finding the initial and final conditions. So I think they put it nicely. Let's just go back up. Oh, this is going to be way up, sorry. Up and away. There we go. First determine the initial conditions and the final value. Right, so now we've done step 1. Step 2 is the cumbersome one. That's the one that takes the thinking, and that's the challenging bit, because this is now where we need to set up the second order differential equation. From that second order differential equation, we're going to get the characteristic equation so that we can get our S1 and S2 roots, and depending on the values of those two roots, we can then determine whether it's overdamped, critically damped, or underdamped. All right, so that is step 2. So how we do that is, first thing that you do, and I call it step 2.1, you first make all your independent sources 0. All your little circle sources, we make a 0. So even though it's now for time after time 0, we now want to just figure out what the response type is. So to do that, you make your source 0. If it was a current source, you'd have to make it an open circuit. So then your circuit is going to look like this. And then what they tell you to do in step 2 is to use KCL and KVL. Let me just zoom in. Apply KCL and KVL. in order to get to that second order equation. Now initially you won't know, now where am I going to start with a KCL or a KVL? So I can't really think of a recipe on how to do it. This is now a bit where experience is going to come in, or where you just quickly look in your head, if I do this, what am I going to get? So this is practice, unfortunately. There's no, okay, first look at this, then look at that. So I'll tell you what my thinking was. So I'm looking at effectively three parallel branches here. I've got the branch on the left, I've got this middle branch, and the branch on the right. So I decided I'm going to start with a KCL and see what happens. So I'm going to do a KCL there at node 1. So I've got the resistor current, I've got capacitor 1 current, I've got capacitor 2 current. So IR, IC1, IC2 all need to add up to 0. Right, then I write it out in terms of their Ohm's law version. So for the resistor, it's just going to be V1 divided by 1. So that's the resistor current. For V1, if you want an expression for the current, it's C1 dV1 dt. So that's the same expression from what we used to calculate the rate of charge in the beginning. So that same equation, C1 dV1 dt. And then obviously for this current flowing through capacitor number 2, C2 dV2 dt. Okay. So remember, my objective is to obtain a second order equation. So the problem now with this equation, number 1 that I've written down here, is you've got how many unknowns? There's V1 and a V2. I need an expression with only V1 or only V2. So I will need now another equation that I can write V1 equals or V2 equals, so that I can substitute that V1 and V2 expression into number 1, and then we see what happens. What equation do we get then? So I did two versions here. You see there's an equation 2 and a 3. So next thing I did, well, I did KCL. So let me write the KVL. And where did I do the KVL? Is just through this one. Okay, so I did a KVL in this loop. So in that case, you're going to get minus V1 plus the voltage drop across that 1 ohm resistor, which is going to be IC2 times 1. So that's that voltage over there, and plus V2. So V2 plus I1C2, so that voltage across those two elements have to be the voltage the voltage across those two elements has to be the same as V1, right? Because that node, they're both sharing that V1 node and the ground node, so the voltages has to be the same. So now I could write an expression V1 equals V2 plus, and then I substitute my IC2 because I want everything in V1s and V2s, remember, with C2 dV2 dt. Now obviously I could have written this as V2 equals, and then in terms of V1. Okay, I would have gotten a bit of a different expression. So you could have gone either way and say V2 equals or V1 equals. So that's the one option. Or two options actually in the one equation. What if we take that same KCL? So I tried another, you see there I wrote the OR. I tried something else at the bottom. I said let's do a KCL again. We use that same expression, but instead of writing the current now in terms, this current IC2 as the derivative of the voltage for the capacitor, let's just use Ohm's law across that resistor, and I wrote that current must also be V1 minus V2 over 1, that expression over there. And then if you shuffle here, shuffle there, you end up with V2 equals 2V1 plus C1 dV1 dt. So now you've got two options. You can now either substitute in our equation 1 the V1, substitute those two V1s with equation number 2, or I can substitute that V2 with this expression for voltage number 1. What did I do? I don't know why, but I took equation 2 and I plugged it into equation 1. If it was today, I would do plug V2 in there and get an expression for V1 and solve that first. So don't ask me why. Either way, it has to work out to get to the same answer. Hey, so let's plug then equation number 2, this one, plug that equation into our equation number 1 there. What are we going to get? Quite a lengthy thing, eh? Because now that V1 is that whole expression, so that's the V1 substituted. So let's see, that expression is the one over there. And then for this one, I need to take the derivative of this expression. So it's dv2 dt and then c2 dv2 dt squared, the second derivative, what you see there. And then that whole derivative, I still need to multiply with that c1, the original coefficient over there. Okay, so we've got the second term in equation 1 covered. And then the third term remains equation, there we go. Ooh, I ran out of space, it seems. Is still this same expression over there, the C2 dV2 dt. Okay, now you need to really keep all your varkies together because now we need to add up the same terms. So let's look for all the second order differential terms. I've got a second order there. I've got no, that's a first order. Second order, it's the only one. It's only that one, but it's C1 multiplied with that term. So it becomes C1, C2, second order derivative of V. Hey, wake up. There we go. Then let's look for the first order derivatives. There's one with C2. There's one with a C1. And there's another one with C2. So I've got two C2s. So there's the two C2s and there's the C1. Those two combined, multiply that with the first order derivative. And then constants, it's only that V2. Only that V2. Okay, so fantastic. That means we've got our second order differential equation, but the key, I don't want a coefficient in front of the second order differential. I want that to be 1. So we take that C1, C2, and we divide everything with C1, C2. See there, you can zoom in a little bit there. So there I've got the C1, C2 and divide by C1, C2. And I can substitute because I know what the capacitor values are. So we substitute and they've chosen it to be very nice values. And we get a 7 and a 6. Right. Now we write this in the form of that characteristic equation. All right, step 2.2 I called it. S squared plus 7s, so the second order becomes the s squared plus 7 plus this, plus the 6 there. So that's an easy one. And then I don't know if you can still do factorization. Yeah, that for you guys it's not that long ago. Eh? For me it's like almost a quarter of a century ago. So for you guys it's just the other day. So you do a factorization or wherever you can do the whole minus b plus minus the square root of blah blah blah, up to you. And you get s plus 1, s plus 6, and you get s1 and your s2 values. Fantastic. And now once you've got this s1 and s2, now you look at them and are they negative? Oh, well, let's start with, are they real? Yes, they're real values. So this means it has to be either a underdamped, no, I'm lying, overdamped or critically damped. But they have to be negative as well. Hey? If you get roots that's a S1 and a S2 value that's positive, you've got a big problem. Then somewhere you messed up. That can't work. So both of them has to be negative. And then are they equal or not? So if they are equal, then it's going to be a critically damped scenario. And if they are not equal, I just want to clicky something here. If they are uneven, that's the nice word I'm looking. If they are uneven, it means we've got a overdamped response. So both of them, they're real, they're uneven, they're negative, we're going to have a overdamped response. So we write down the overdamped response equation, but note it's V2 transient. Right, so we're busy working with V2 now. So it's V2 equals, but not just V2. It's not the complete response. This is only the transient response. Why? Because up here we made the source a 0. So we took out the step response part of it and made it a natural response in that sense. So this part is only the transient response. Very, very important. Okay, but we know the format of that for the overdamped case. So what do we need to solve for is A1 and A2. And then we also, remember, we need an expression for V1. And now we're going to go back to this equation, our equation number 2 that we used. And now that we've got an expression for V2, we can substitute it into equation number 2, which is what I did over here. And take that expression and then take the derivative of that expression, shuffle a little bit, and you get the new coefficients. When I looked at this again this morning, I couldn't figure out why I just didn't, we just added up those. Let's perhaps quickly do that somewhere. Comment, where's the comment bit? This will just make life a little bit easier now, eh? Because now if you're gonna, how big is that going to be? So in A1 minus a third of A1 is just 0.666 A1 and 2/3, and on this side you've got A2 minus 2A2, so it's minus A2. Right, so you could have actually simplified it a little bit more over there. Okay, back to this one. Alright, so that's 2/3 there. 66666, so how many you want to put there? Okay, so that is, for now we've got an expression for V2, we've got an expression for V1. In both cases, it's only A1 and A2 that needs to be solved. So only two unknowns. Right, so now the steady state response, that's the textbook step number 3. Let's just go back to the textbook. So obtain the steady state response. So what is XS? X at time infinity. So we already know that for V2 infinity, it's 35 volts. We determined that in the previous page. And now step 4 is get the total response. So the total response, remember, is steady state plus transient. Steady state is 35. Transient, we just got the expression at the top there. So now, like in all the previous examples, now we're going to use V0 at time 0 plus and dV/dt at time 0 plus to solve for A1 and A2. And at this point, you've got two expressions, two equations. So you could have chosen which one do you want to use. Do you want to use your initial conditions for V1 to get A1 and A2, or do you want to use the initial conditions for V2 to get A1 and A2? It'll work out the same. So I stuck with V2. So now I use V2 0 plus, and I get 35 plus A1 plus A2. Wait a minute, equals 0. Yeah, sorry, I was just confused for a moment. So the initial condition was 0, and then 35. The S1, okay, I noticed there now, I put the S1 and S2 in there. Well, that happened there already. So S1, there's the minus 1 in front of the T, and the S2, there's the minus 6 in front of the T. So T is now 0, and the exponent of 0 is just 1. So I get A1 and A2, so I get a first equation with A1 and A2. It's minus 35. Now I use this first order differential initial condition. So I take the differential of this expression, minus 1A1 e to the minus 2t, minus t, and minus 6 A2, and the exponents are just again 1. The rate was 0 for dV/dt, so I get a second expression for A1 and A2. And now how you want to solve them, that's up to you. The quickest way is if you look at equation 1 and equation 2, if I subtract the 2, I get rid of A1. and I'm left with 5 A2s must equal 35. So I said equation 2 minus number 1, and I get A2 is 7, and then that, which means A1 is going to work out at minus 42. So now I have my A1 and A2, so I can now write the complete expression for V2, and then you can go and work out the complete expression for V1. And now you're not even done yet, because what is it they're looking for again? They're looking for V0, this one. Whoa. We're looking for V0. So all we have now is V1 and V2. Now we need to subtract those two expressions so that we can get what they're actually looking for in this V0. So let's go down again. So we've got those two expressions. We subtract them, and you get 14 minus 14e to the minus 6t. So this tells you what that voltage across V0 will do. Now, what does this look like? If you're going to plot this now. So let's just look at this, if this is going to work at time 0. Because remember, the initial voltage across the initial current through that resistor was 0 amps. There was no current flowing. So the initial voltage across that resistor would have to be 0 volts, right? So if we substitute a time 0 there and a time 0 there, you get 1 minus 1, and you get 14 times 0, which is 0. And then at time infinity, again, this goes to 0, this goes to 0. So you've got a 0 times 14 again, and yeah, it goes back to 0. So there will be something happening. Now, if you were to plot it, you get this. How long have I? The recording is actually not going to be that long. When you plot that, so I've got, let me just make this a little bit smaller. And still, I need the, there we go. I hope you can still, yeah, we can do it like this. So we've got, I've plotted the voltage V1, that's the blue, and the orange for V2. And then subtract the two to see what happens across that resistor. Now notice, I wonder if I zoom in like really close. The initial rate of charge of the number 1 was 70 volts per second. So that would be, if you were to draw a straight line there, the gradient of that initial charge. What was the initial rate of charge for capacitor 2? The orange one, well, that yellow line is now in the way a little bit, but it comes out like this. So initially it was 0, but you can already see from this graph that it's just for that split second, that it was 0 volts per second. The moment that capacitor 1 has some charge, capacitor number 2 will start charging. All right. So they charge, but their voltages are never exactly the same until a very long time. Oh, well, not a very long time. Well, where do we have? About 5 seconds there. After 5 seconds, they both have the same voltage. So what we've got in this yellow is our V0, the one that they're actually looking for. So this is actually, since V0 is across that 1 ohm resistor, that V0 actually tells me what the current is through flowing into capacitor 2, or that's flowing through the resistor and the capacitor. So it starts charging really fast. So you see there, it starts at 0 amps. Okay. So we said initially nothing, there's no charge going into capacitor 2 at time 0 plus. So because the current starts there, you can see the current starts there at 0. But it starts very quickly, hey? And then up to this point. And then it starts slowing down. So what does it tell me? That at this point of maximum current, there is the point in time where you've got a maximum difference between the blue and the orange line. After this point, those two graphs, or the gap between them, so that distance, vertical distance, starts getting smaller and smaller and smaller, and you can see as that gap gets smaller and smaller and smaller, the current starts getting less and less and less until eventually both capacitors are charged up to 35 volts, and it goes to 0. Alright, so that's in terms of electricity. Where is this one now? Yeah, that's the lecture notes. Oops, that was not the button I wanted to push. But anyway, okay. I want to finish this with a waar is ons nou? Ek wil nou daai prentjie. Okay. So this is for you guys that I need to be careful now. Hey, the more hands-on people like me. So I like to, when I look at a circuit, I like to visualize it with something I can see and understand. So let me share the screen. There we go. So what I've drawn here is our, let's put it like this. There's our source, our 35 volt source, and it's a dam. But it's a, you see this dam, it goes on. It doesn't, for you guys, that direction. So it doesn't empty, okay? It can't empty. Think of it as the Val Dam or something. But then next to it, I put in two containers, and then this is our C1, this will be our C2, and C2 is a little bit smaller than C1, capacitance, capacity, you know, capacitance, capacity. So why do they call it capacitance, by the way? For a dam, we know if you talk about the dam's capacity, everybody will give you, oh, the units must be in liters, right? Or cubic meters, if it's a big dam. But if it's a capacitor, it has a capacitance, a capacity to store electric charge, right? Electric charge, volts. So now what we're going to do, when that source switched on, we're going to open this valve and open this valve. Now valve represents, this is our two 1 ohm resistors, okay? Both of them 1 ohm resistor. Now perhaps you can't visualize this because you've never seen it happen. I think you'll only be able to visualize if you've seen it in some way. But now if I were to open those two valves exactly at the same moment, open them, we know that you will immediately have water start flowing into this first dam, our first capacitor. How much will be flowing into the second dam? Nothing yet. Why not? Because you can't have any water flowing into this capacitor unless you've got water in this dam. There has to be water in this dam to flow over to the second dam. Okay, so you've got water flowing in this one, but the moment that you've got water, I should have actually put those valves right at the bottom for this to be more true, I think. The moment that you've got water flowing into the first dam, you'll have water start flowing into the second dam. But dam number 1 will always be just a little bit ahead of dam number 2, but it will start catching up, eh? Just like those two curves, which one is it now? This one. Just like these two curves, they start catching up with each other. In the same way, those two dams will start catching up, and eventually, once they filled up, they can't fill up beyond the level of that dam. All right. That, I think that everybody can understand. Okay, so they can't fill up beyond 35 volts, or in this case, whatever that height of that dam is. If for the only way you can get that to happen, for these to be higher than the first dam, is you'd have to do what? Yeah, you'd have to put a pump over there, and then the pump creates a pressure difference between the two, hey, so that these two dams can go higher. But with just valves, both of them have the same pressure from the top, so yeah, it's not going to go higher than the others. Okay, that is it for chapter 8.7 and chapter 8. We're going to start then in the next one with chapter 9. So chapter 8 or the whole of chapter 8 really is, hopefully you've seen, it's just a recipe. Step 1, step 2, step 3 that you need to follow, and then identify the right circuits. So the only way you can't do chapter 8 is if you can't do circuit analysis. If you get your series or parallel wrong, if you typically other mistake is where you swap the polarities the wrong way, you write the currents in the wrong direction, then things start going seriously wrong. So in a sense, you just need to work slowly. Don't rush through these problems. All right. What's that saying? Haste makes waste. So work slowly. Don't rush it when you're going to work through these. But for me, chapter 7 and chapter 8 should be a freebie for you. Well, this whole course. So it shouldn't be that hard, but again, it's practice. You need to really practice that in. Okay, so if you've got any questions, if you get stuck with the homework, or if there's something in any of the practice problems that you don't understand, remember for the lectures, for the practice problems that we did in class, please post your question on the discussion board for that specific lecture. If you rather prefer, I explain it to you over a video call, and you can share your screen and you can show me what you actually did and tried, and then we can discuss that. You're welcome to then book via that Google form. So you go to consultations, and under my name or under my photo, there's that link that you can click, and you can just book a consultation there, and then we can discuss and I can see where you get stuck. But I have to see what you tried. Okay, you can't just tell me I don't understand the problem, because then I'm just going to say I don't understand your question. Okay, you need to at least show me where you got stuck, and then we can work it from there. Fantastic. Right, so we're done with the first two chapters, starting with AC, or just phases, the introduction for AC circuits. We'll start then in the next lecture. Thank you very much. Bye-bye.